The trend of AI really accelerated the importance of availability. One failure costs around 700,000 euros on average. You want to optimize the reliability margin of your whole system. We developed a solution called Power System Reliability Modeling. We really think like a stepwise approach is the key to implement health monitoring for customers.
This is the podcast for engineers, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. I'm your host, Peter Ballant, and we continue our journey into the world of powering AI. Today we're sitting with Christian Bernhardt. Welcome. He's a system architect at Infineon. So glad to have you here today.
Thanks for having me.
You're welcome. You know, when we talked offline, you mentioned this concept of availability and the availability of servers and services. And I got to thinking, how does this feed into this whole idea of powering AI? Maybe you could bridge this for us.
The trend of AI, like ChatGPT, generative AI use cases, really accelerated the importance of availability. And the reason is why is because the way how data centers are utilized changed with this new introduction. Like historically speaking, like data centers usually hosted like websites, and there were like web application hosted on a lot of different servers around the globe. Like, and now if you think about like Black Friday, for example, like the owner of those websites really wanted to state them like that they are available now, but they could prepare for something like that. So, for example, like Black Friday was coming in, they bought extra bandwidth with a lot of different servers, and therefore they were optimizing their reliability. And if the server went down, they had a lot of different servers as well, where like the web application was still hosted. Now, with AI use cases, you have basically for one individual AI use case an orchestration of hundreds of different AI acceleration cards. And they are doing this in parallel. And if now one of them fails, if this computation fails, like two things could happen. Either the whole computation breaks down and like you have a faulty result, or you need to restart the computation. And those are very, very costly events.
Okay. Now you talk about these failures. What is this? Does this happen often that there are
Yeah.
failures?
Yeah, it's you always have to put it into perspective. Like in general, failures in semiconductors and power supplies are very rare. But I think like Danny Clavette in a previous episode did a very great job in explaining how many like power supplies you actually have in the field. Like just as a short summary, like you have 800 data centers, soon to be 1,000, and in every data center you have like 10,000 racks, and within one of those racks you have 10,000 of power semiconductors and passive components. Now, one component of this fails, it could mean that the whole server goes down, and here it's because of the numbers, not that unlikely. And you have like to give you a rough like number. In the Open Compute Summit, somebody told us that every 26 minutes, one power supply can fail. And one failure, which includes then also a downtime, costs around 700,000 euros on average.
Wow. Okay. So this is like the old school failures, but under a magnifying glass.
Yes,
Yeah.
absolutely.
Incredible. So what were some of the traditional ways of optimizing availability in the past?
Yeah. I mean, there are a lot of different angles you can tackle this issue, and a few of them Infineon doesn't even contribute to. Like, for example, like any complex machine, the operators need to be able to operate them. So human errors like cause a lot of failures. So therefore, like the operators are very well advised to train their staff to maybe not drink coffee right next to the AI server, right? But there are also like with the trends of AI servers where the power density is increasing significantly. This also has as an implication that the temperature within this AI servers is increasing. And a general rule of thumb is that for every 10 degrees more temperature, the lifetime of your device will be halved. So thermal management in data centers is one of the key issues, even getting more important in AI servers. Also, there are a lot of ways how to optimize reliability where we as Infineon play a very crucial point in enabling our customers. One, also I can just recommend the podcast episode with Roberto Isolati, where he talked about the right choosing of power topologies, because the right power topologies have an impact on their efficiency, and the efficiency of the power supply also indicates how much heat is generated in the power supplies just because of inefficiencies, essentially. So, and this excess heat needs to be get out of the power supply again. So you're optimizing really by choosing your power supply reliability, by selecting the right topologies is key. But also, and it's sound reliable in design and selecting the highest reliability components. And what is basically like a example of this would be that you want to optimize the reliability margin of your whole system. And the reliability margin is essentially like what you would expect your normal operation conditions is, and under which operating conditions your power supply will fail. The difference between those two like operational points is your reliability margin. So if you have like a bus voltage of 48 volts, you can choose a capacitor which is rated for 50 volts. But I mean, you only have a reliability margin of 2 volts. So I wouldn't sleep well at night if I design it like that. But what you can do is that you select a capacitor which has like 63 volts, but this capacitor is more expensive, right? It's bigger. So therefore, it's always a trade-off with this traditional reliability methods, basically between your cost and the reliability.
But as we have seen, the power supplies nowadays are getting much smarter. Is there any way to incorporate the smartness of the power supply into reliability
Yeah.
measures?
Yeah, absolutely. I mean, like digitalization enables new use cases across all industry, and this is also the same for the reliability. Like two very like almost buzzwords I would like to say are health monitoring and predictive maintenance, and both of those like trends really can enable increase of the system's reliability.
When we talk about this topic of reliability in an
Mhm.
AI server environment, for example, we often hear this term health monitoring. Can you tell us a little bit more about that and um, what exactly is that in the semiconductor realm?
Mhm. Yeah, absolutely. So, health monitoring in itself is basically the system tells you how healthy it is. Like a very like example where you can see this around is just in your smartphone. If you go to settings, you can see like what is the health status of your battery. And this is basically the battery telling you I'm that healthy. And now to enable this for power supplies, you need to basically have two very important aspects. One is you need to know how the power supply or the battery was operated, and the average over the operation is basically we call it mission profile. So you know need to know the mission profile, and you need a very good description of what affects your reliability or your health of the power supply. We call that a model, so a health prediction model. And with those two aspects, you can make your health prediction. To give you like an example, like for the battery use case, for example, the operating conditions would be how often did you charge your phone? Like how deep was the discharge? What was the average ambient temperature? And what was the peak current that you consumed? Like all of those factors affect the reliability of your battery or the lifetime of your battery. And now the reliability model, the health monitoring model, basically describes how do you need to combine those individual parameters to get to the health status of the overall power supply.
Okay. But how can you now use this health status parameter?
Yeah, yeah. So like the major use case is predictive maintenance. Predictive maintenance is essentially a data-driven method to optimize your reliability of the systems and optimizing it for cost, essentially. Like a very tangible example would be how you do your maintenance on your car. Like with a car, if you drive it and then it breaks while you are driving it, that's very expensive. You need to get the car to the workshop. It needs to be repaired. You need to have a new car essentially for the meantime. So this is what we call reactive maintenance. Then we have periodic maintenance. And periodic maintenance is essentially once a year you go to your car dealer and do like a checkup. And so here you basically improve the reliability of your car, but it might be actually not necessary. And then we have prescriptive maintenance. Prescriptive maintenance is the car manufacturer telling you every 120,000 kilometers you need to change your brakes. And then you do that. Predictive maintenance now would be basically a sensor over your brake telling you exactly when is your brake in a state that you need to do your maintenance. This could be either 140 and you save a maintenance cost essentially, or it could be like 100 and then you need to go to maintenance early to prevent actually a critical failure. Same logic applies to power supplies. And another use case that we see, which becomes more and more important over the time, is that a health status enables circular economy. Like, because if now the power supply vendor or any OEM gets his system, he needs to make the decision: do I want to resell this? Do I need to repair this first, or do I just recycle it? And therefore, he needs to know like how healthy is actually the system, what makes the most sense for me. And so here, using this health status parameter can enable circular economy use cases. And in the end, all of them play into optimizing the total cost of ownership. Like, because with a very effective health monitoring and effective maintenance strategy optimization, you can you reduce your capital expenses as you need to buy less equipment, and you optimize your operational expenses because you prevent failure from happening and you optimize your maintenance.
Okay. I'm wondering, technically, speaking, what does this health monitoring solution look like, actually?
Yeah. Yeah, the devil really lies in the detail, and it can get very nuanced. But generally speaking, you have two different types of maintenance, or a first important distinction that we have to make. One is you have it locally, or the other one is you process it centrally. So the difference essentially is that on a local system, like for example, a wind turbine, the wind turbine is checking itself, like what is my health status, for example. And then when it sees, hey, my health status is not very good, it might like reduce the maximum power output to ensure I don't break until the next maintenance interval. And then like the decision is being made like, okay, I do maintenance now. The central way would be that the wind turbine is quote unquote stupid and it just broadcasting their data to like a management system, to like a central, like to a cloud. And then on the cloud, there the operator does the calculation to detect the health status. So it's basically like on the edge and the other is in the cloud, right? And yeah, those would be like the two major differences. For the local processing of the health status, we call it in situ because it's happening in the device. And ex situ is basically then the reliability model or the health prediction is happening outside of the device. So therefore, ex situ.
Okay, so you've explained ex situ and in situ, but what are the implications of each one?
Yeah. So essentially, in situ here, especially in the realm of power supplies, you have the major benefit that you have all your operational profiles in very high resolution, like all your system parameters. The drawback to that is essentially that you don't have that much computing power. So you cannot run the most sophisticated and complex algorithm to actually process the status. But on the other hand, like in ex situ methods, you have all the computing capabilities that you require. But what you don't have necessarily is very high resolution data. So it's like not one has like the by far the upper hand. It's just like how do you want to do your health monitoring? And like the three major methods how you do your health monitoring would be essentially statistical, would be based on physics on failure, and would be anomaly detection. And those, like, maybe I will briefly go through all the three methods. So the statistical model is that you collect a lot of data, and then based on like mission profile data, failure data, and then you analyze this data. You know, based on the normal usage, when do my failures happening? And then you make a statistical analysis out of this. And then, like, you do your health prediction that you essentially say, I measure now the behavior of my current device, or I measure how my device has been used, and then I compare it to my expected statistical behavior. And based on this comparison, you can make an estimation how healthy it is. Physics of failure is here a method where you really need to know everything about your component. It's essentially like, I know my power supply breaks exactly after this time because like the solder cracks. And okay, my solder cracks after a certain number of thermal cycles. And now in your device, you count the number of thermal cycles. And then in your lifetime model, you basically say, I had this number of cycles. Now my device is this healthy. Actually, but getting to this level of understanding about your system is really, really complex. Last one is anomaly detection. And anomaly detection essentially says, this is now the baseline behavior that I would expect from my device. And now something happened, and now the device is working abnormally. Like it's not working the way I think it should behave. And then by the comparison of those two behaviors, you can say whether your device is healthy or is not healthy. Thing is here also very complex to determine what is a normal behavior and what is an abnormal behavior. That's there the devil really lies in the detail. Yeah. Yeah.
Okay, so several approaches, but can you give me the global view now of what Infineon can offer
Yeah.
in this area of maintenance prediction?
Absolutely. Absolutely. So we developed a solution called Power System Reliability Modeling. What we do there, it's statistical approach, which is in situ executed. And the way how our solution is working is that we have the fit parameter of all the components that you use in your design. And every fit parameter is the failure in time. And every parameter now ages faster or slower depending on how it's used. Our digital power controller, which is basically the product of power system reliability modeling, is measuring in real time what the temperature, what the electrical stress, like the voltage and the current is, and accelerates each and every single component based on those measurements. And then we can calculate the overall failure rate of the power supply. And this power supply failure rate parameter now can be used to do a health estimation for the whole power supply. And for us, it was really important that we set a focus here on availability, essentially, like that it's easy to implement. So therefore, our solution is topology and power level agnostic.
Okay. So just another example of how Infineon is committed to powering AI.
Yes,
Yeah.
absolutely.
Okay, good.
Yeah.
So final words from you.
Yeah. What I think like health monitoring, especially in the beginning, is a very complex application which has huge upside when it's implemented correctly. But this initial level of complexity is overwhelming a lot of customers, a lot of people. We really think like a stepwise approach is the key to implement health monitoring for customers. So from 0 to 100, it will most likely be a bit too complicated. But with our solution, you get like a very first, very good health monitoring solution, which also helps you to understand your data, so your operational of your power supplies even better. So if you are interested in the topic, would be very happy to support you on this journey to really enable predictive maintenance for your systems. And if you're interested in it, like in general, into a deep dive, feel free to visit our website, where we have a lot of collaterals available where you can go in more detail.
Excellent. I say thank you for coming in today and sharing your knowledge with us and with our audience. And I also say thank you to our audience for listening to today's program. We're constantly looking for ways to bring you better content. So if you have any ideas, please send them to wepowerai@infineon.com. So thanks again, and we'll see you soon.